All right, class, we've arrived to exponential and logarithmic equations. So using one-to-one property for exponential functions to solve exponential equations. So for any algebraic expression s and t and any positive real number b cannot equal 0, if b to the s is equal to b to the t, if and only if s equals t. So what this is basically telling us is if our bases are the same, and we have a base is equal to the base, and the only difference are the exponents, it tells us that the exponents must also be the same. So let's take a look at this first problem here. Notice that we have a base of 2 here and a base of 2 here. So because our bases are the same, this tells us that I can set the exponents to each other. So then I would get x minus 1 is equal to 2x minus 4. Okay. So we're going to go ahead and subtract x from both sides, and I'm left with negative 1 is equal to x minus 4. Add 4 to both sides, plus 4, and we end up with x is equal to 3. Okay, and so that's what we wanted to find. What is that x value? Take a moment to try b. Well, notice here, our bases are not the same here. So does that mean that it's not possible and we have no solution? Well, what we want to really think about is, can I then rewrite these with a very similar base? So let's look at 8. What are the factors of 8? Well, 8 is 2 times 2 times 2, right? Because 2 times 2 is 4, times 2 is 8. So this is the same thing as saying 2 to the third power. If I look at 16, what are the powers of 16? The factors of 16, sorry. So 2 times 2, because I get 4, times 2 times 2, which is 2 to the 4th, okay? And if it confused you how I came up with these 2's, another way you can kind of think about this is think of a factor tree, right? 8, I do 2 times 4, I bring down this, and I get 2 times 2. Same thing with 16. I can do 16, 2 times 8, and 8 is 2 times 4, and 4 is 2 times 2. So same thing. So that's essentially what I did, just horizontally. So that means I can rewrite this base 8 and 16 with a base of 2. So it would be 8x plus 2 is equal to 16x plus 1. So what I'm going to do is I'm going to rewrite it. So instead of writing 8, I'm going to write 2 to the third power. And instead of writing 16, I'm going to write 2 to the 4th power. But then let's go ahead and keep those original exponents. I have x plus 2 here, and I have x plus 1 here. Okay. All right, so then that tells me that I can go ahead and distribute this 3, and I'm going to distribute this 4. Because now I do have the same base, except it's going to look like 3 times x plus 2 on this side is equal to 4 times x plus 1 on this side. Okay. So then I'm going to go ahead and distribute this, because now I have a base of 2, so this becomes 3x plus 6 equals 4x plus 4. Let's go ahead and solve this. So I'm going to bring the 3 over, so subtract 3 from both sides. And I end up with 6 equals x plus 4. Let's go ahead and subtract 4 from both sides, and I'm left with x equals 2. Okay. All right. What about this one? I have 2 to the 5x equals the square root of 2. Try this one out, see if you can figure it out. All right, so for this one, the trick is to remember that the square root of 2 can be rewritten as 2 to the 1/2. So now they can, in fact, have the same base. So we're going to set those exponents equal to each other, and we end up with x is equal to 1 over 10. All right, last one. Oops. Let's see. D, go ahead and give it a try. All right, so unlike the other ones, for D, we are not able to write 3 and negative 2 with the same exact base. So we can't use this property that we were using, so we do need something else. Okay, we're going to talk about what that something else can be. But for now, with this property, we can't do it. Okay. So sometimes the common bases, just like we just saw in the last example, cannot be found, which is the case we need to take a new approach. So given an exponential equation in which a common base cannot be found, solve for the unknown, apply the logarithm to both sides of the equation. If one of the terms in the equation has a base 10, use the common logarithm. If none of the terms in the equation have base 10, use the natural logarithm. Okay. Use the rule of logarithms to solve for the unknown. So let's take a look at this first example here. Okay. So I don't have a common base here. So what we want to do, so we can't find it, we're going to apply the logarithm. So we're going to ln both sides. Take the log of both sides. Okay. So we're going to take log of 5x plus 2 is equal to log 4x. So now we can use the power rule to bring these powers to the front. So we're going to end up with x plus 2 times log base 5 is equal to x times log base 4. Okay. So now let's go ahead and distribute here. We're going to go ahead and distribute the entire logarithm. So we're going to get 5 times log base 5 plus 2 times log base 5 is equal to x log base 4. Okay. So let's go ahead. Oops, this is supposed to be an x. I don't know how I accidentally dropped that. So let's go ahead and isolate x to one side. So we want to get all the x's on one side. So let's go ahead and move this guy to the other side. So we're going to subtract x log of 5 from both sides. So then we are left with 2 log base 5 is equal to x times log of 4 minus x log base 5. Okay. So here, notice, what do these two have in common, right? So they both have an x, so we can use our favorite F word, which is factor. So let's go ahead and factor out that x. So we end up with x outside of log of 4 minus log of 5. Remember, this is 2 log 5. Okay. So now we factor, what do we want to do? We want to be able to get x fully isolated. So we're going to do that by dividing now by log 4 minus log 5 on both sides. And so we're left with x equals, and it's going to be 2 log 5 over log 4 minus log 5. Okay. So if we go ahead, we can plug this into our calculator. So in our calculator, I'm here at the scientific calculator for decimals. We're going to come over here to functions. We are going to take, so it's going to be the quotient. So let's go ahead. Actually, we're going to come back over here. We're going to do 2 times. Now we're going to do log. Go back to our main. We're going to do 5. Close that. We are going to divide that. And here we do need to put parentheses because it's an expression underneath. So that expression is going to be, we're going to come back over here. We're going to have log of 4 and close that parenthesis minus, go back to function log of 5, and we're going to go ahead and close that and then hit enter, and notice that we get negative 14.4251. Okay. All right, so something I want to kind of note, both of these are the correct answer, right? This one here, this is what we call the exact answer. And this one is what we call an approximation. That was weird. That's the approximation. Okay. All right. Go ahead and try the next one on your own. All right, so for this one, we did have to do a little bit of solving prior for us going ahead and applying, the natural log to both sides. So go ahead. The first thing we want to do is definitely divide out that 20. Our goal is to isolate e first, and then we're going to use the inverse of e, which is going to be our ln function. Once I've divided out the 20, right, to kind of reduce this, so I have e on one side, I'm isolating the e value. Right, I'm left with 5, so 100 divided by 20 gives me this 5. So now I'm going to go ahead and apply ln to both sides. And in doing so, I end up with ln of 5, and then I can use the power rule, so I can bring that exponential value 2t to the front, right? And then I'm left with ln of e. But ln of e, right, is one of our properties that we have. It is one of our properties that we have, and we know that this whole ln of e is just equal to 1. So this becomes 2t times 1. So now I can divide both sides by 2, and I end up with the exact value of ln 5 over 2, or an approximation of t is approximately 0.8047. All right, try the next one on your own. Remember, isolate the e first. Remember, our goal is to isolate first, so we're going to start off by moving that 5 over, so we end up with 12 minus 5, which gives us the 7. And then what we can do once we have that 7 is we're going to go ahead and divide out this 4 to get e by itself. So we end up with 7/4 on this side. So we end up with 2 to the ex equals 7/4. We're going to take the ln of both sides. What's happening here? And now, because we've taken that natural log, we can bring that power into play here. So we're going to bring that 2x out to the front, that power property. That's what I was thinking of. And notice that we have ln of e. We have another property that as long as the base is equal to the input, that's going to equal 1. And so we end up with 2x equals ln of 7/4. Divide by 2 on both sides. And this is our exact value. Over here we have our approximation. All right, so hopefully you were able to follow that on your own, and you got the same answer. All right, using the definition of logarithms to solve logarithmic equation, sorry. So here, for an algebraic expression S, the real numbers b and c, where b is greater than 0, b cannot equal 1. So if the log base b of s is equal to c, if and only if b to the c power equals s. So basically using that logarithmic definition and how it's associated and is the inverse of the exponential function. Okay. All right, so let's take a look here. We're gonna isolate the ln. So let's go ahead and subtract 3 from both sides. So we're left with 2 ln x equals 4. Now we're gonna go ahead and divide both sides by 2. So we have ln of x is equal to 2. So in order for us to find out what x equals, we're gonna use the definition, which tells me that I'm gonna take the base, which remember, this is in case you forgot the natural log, the base is e. It's going to be raised to the second power, and it's going to equal the x. So we end up with e squared is equal to x. And this is what we would call our exact value. And then if we approximate it, you can plug e squared into your calculator, and we'd end up with 7.3891. And that's our approximation. All right, here we have another one. Go ahead and give this one a try. All right, so for this approximation, first thing again, always isolate that ln. So we end up with ln of 6x equals to the 7 halves. Remember, ln is base e, so using kind of that definition of logarithms, we're going to get e to the 7 halves equals 6x. Divide both sides by 6x here. And then we end up with our exact value of x equals 7 halves divided by 6. If we approximate it, we end up with x equals 5.5192 is our approximation. All right, so hopefully that wasn't too difficult, but always reach out if you have questions. Let's go ahead and try one more here. in this particular case, what we're going to do, actually the instructions got condensed. We're going to go ahead and make sure that we are condensing. So we're going to condense here in order for us to attempt to solve it. So because I have multiplication here, right? I'm sorry, addition here. This is telling us that we do have the product rule. Okay, and so let's go ahead and take a look at that. So this is going to be log base 2. So this allows me to use the product. So here's 2 times the inside's 3x minus 5 is going to equal to 3. So let's go ahead and write this out. So let's distribute this. So I would get 6x minus 10 is equal to 3. So now since I have it as one logarithm, notice that my base is 2 here. So since it's 2, remember it's going to be 2 and it's going to be raised to the 3rd power, and it's going to equal what's in here. So we're going to end up with 2 to the 3rd power is equal to 6x minus 10. Okay. Well, 2 to the 3rd power, that's just 8 equals 6x minus 10. Let's go ahead and solve this. We're going to add 10 to both sides, and we end up with 18 equals 6x. We divide both sides by 6, we see that x equals 3. So we want to make sure that the inside of both of these logarithms are positive, especially when we use the product property. So when this happened here, we want to make sure that we go back to the original and make sure that both of our logarithms are going to be positive. So log base 2 of 2 is, yes, going to stay positive because I didn't change anything in there. But log base 2 of 3x minus 5, right? Will that still be positive, right? So we want to make sure that this stays greater than 0. So let's go ahead and plug it in. So 3 times 3 minus 9. And here, sorry, minus 5. 3 times 3 is 9 minus 5. That gives me a 4. And 4 is definitely greater than 0, so we are good. Okay? So it's always good for us to check those values. Go ahead and take a moment and try D. All right, so for this one, notice that we're using the quotient rule. So we're going to first condense, and I wanted to write some steps over here for everybody. So we're looking at the first step is to condense. So that's what we're doing here by using the quotient rule. Our base is 4 here, so we're going to take 4 to the 2nd power, and it's going to set equal to what our input was there, which is x plus 2 over x minus 4. Let's go ahead and simplify both sides, multiply both sides by that x minus 4. X minus 4 on the right-hand side cancels out, and so now we're going to distribute that 16. We end up with 16x minus 64. Go ahead and isolate your x, right? And go ahead and solve for x. And when we solve for x, we see that x is equal to 4.4, sorry. So the last thing we really want to do is we want to check. Again, we want to come back over here and check to make sure that what's inside that logarithm is positive. So x plus 2 is greater than 0. So if I plug in 4.4 plus 2, that's going to be greater than 0. If I plug in 4.4 and I subtract 4, turns out that is also going to be greater than 0. So we are good, and that answer definitely works. I wrote down the steps on this side just to kind of highlight, and I think I forgot 5 because 5 really should be, we want to check our x values. But we have condense, right, which means get everything together. Then we're going to isolate our ln function. We're going to write it as an exponent, which is what we did here. And then we're going to solve for x, which is the rest of this. And lastly, we're going to check for those x values, make sure that they're positive and they're within the domain. All right, let's go ahead and learn the last thing here before we end this section, which is looking at using the one-to-one property of logarithms to solve logarithmic equations. So when we're looking at this, we have log base b of s is equal to log base b of t if and only if s is equal to t. So this is kind of very similar to what we talked about with exponentials. If the bases are the same, we can set the exponents to be the same. If the bases are the same for logarithms, we can set their insides to equal each other. So let's take a look at this first one. Notice I am looking at the natural log of both of these, which means that now, because I'm looking at both the natural logs, so the base is the same, I'm going to be able to set the insides of these natural logs to each other. So I'm going to end up with x squared is equal to 2x plus 3. Okay, so then what I want to do is I'm going to kind of isolate and move everything to the other side. So I'm going to end up with x squared minus 2x plus 3, set this equal to 0. Let's go ahead and factor this. So when I factor this, I end up with x minus 3 and x plus 1 is equal to 0. So this tells me that x is equal to 3 and x is equal to 1, negative 1. Okay, so those are our values. So now, before we move on, though, we do need to check to make sure both of these values work inside of our logarithm. So when we plug this in, if I plug in 3 here, 3 squared, right, that's still going to be positive. So in terms of ln of x, let's do it this way. Let's make a quick table here. And then my other one is ln of 2x plus 3. So if I plug in 3, I definitely get a positive here, right? If I plug in negative 1 here, because I'm squaring it, it's going to be negative 1 squared, right? Which is positive, so I'm okay. So that's positive. So now I'm going to plug in 3 here. So that would be 2 times 3, which is 6, plus 3. So that's still positive, which is good. I'm going to plug in negative 1. So 2 times negative 1 is negative 2 plus 3. That's still positive. So we are set and we are good. Our answers check out. Okay. All right, go ahead and try B. All right, so for this one, again, I have the base. Those log base 2s are the same, so I can set the insides equal to each other. So I get 2x plus 1 equals 3x minus 5. I end up with x equaling 6. So I just need to check when I plug it in, 2x plus 1. If I plug in 6 there, I do get a positive value, so that works. If I plug in 6 here, 3 times 6 is 18 minus 5. That's also a positive value. So it checks out. So our answer is, in fact, 6 equals x, or x equals 6. All right, let's take a look at the last one here, and this is how we're going to kind of end this section here. So for this particular one, we want to solve it, but notice the first thing that we want to do is we want to condense. So let's go ahead and condense this. You know, when you can condense, you should condense. So this will become ln of x times x plus 5. And this is going to equal to ln of 12x. So notice I can simplify the inside here. So I can have ln of x squared plus 5x is equal to ln of 12x. Because I'm looking at the logarithm of the same thing, both of these are ln functions, so that tells me that I can take the insides and set them equal to each other. So then I end up with x squared plus 5x equals 12x. Okay, so let's go ahead and solve for x. So I end up with x squared minus 12x plus 5x equals 0. So here we end up with x squared minus 7x equals 0. So let's go ahead and factor this. So I end up with x times x minus 7 equals 0, which means that x equals 0 and x equals positive 7. Again, we got to check these, right? So notice that when I check this and I plug it in, I'm going to now check it against ln. So I have to check it against ln plus 5, ln of x, and ln of 12x. And so we want to make sure that all of these work out. So I'm plugging x equals 0 and x equals 7. So when I plug in 0 here, that's positive, so I'm good. But when I plug in 0 here it's going to be undefined because remember, I want that to be greater than 0, not equal to 0. So because I'm using just ln here, it doesn't work here, so therefore this answer doesn't work. It only takes one of them to not work, and then the whole thing doesn't work, right? It wouldn't have worked here either, because we would have gotten a 0, because it would have been 12 times 0. Let's check x equals 7. So if I do 7 plus 5, that's going to be positive, so we're good. 7 itself is positive, and then 12 times 7 is positive. So this tells us that the only possible value that answer to this problem is going to be x equals 7. Okay, so x equals 0 would be what we call an extraneous solution, and it would not work here because it's not within the domain. All right, that's the end of this section.